Next, next topic is the pipe flow rate measurement. The first is the pipe flow rate meter. A device for measuring pipe flow consists of the first is the orifice meter, the second is nozzle meter and venturi meter. A principle applied for this device is the reduction of the cross-section area, increase the velocity and decrease the pressure. Then the difference of pressure is used to estimate the flow rate. Okay. And no account for the viscous effects. And we apply the boundary equation between point 1 and point 2 on the horizontal pipe line. That is this is point 1 and point 2. And from boundary equation, because of datum is on the center line of the pipe, so Z1 and Z2 is equal to 0. Assume the head loss 0. So this reduced to first equation. And next, from quantity equation, we can from Q1 equal to Q2, we can derive that velocity at point 1 is equal to B beta square times B2. And from this, we substitute B1 in this equation. Okay. And we got the different pressure between P1 and P2 equal to 1 over 2 G V2 square subtract beta power 4 V2 square. And we rearrange this equation to get V is equal to 2G, the difference P1, P2, and divided by 1 over beta power 4 square root of this. Okay. And we can write equation of the Q is equal to area at point 2 times V2. So we got this equation for flow rate. Another way we write the V2 is a function of V1. We use alpha to represent the D1 over D2, and we can got the V1 and Q1 is similar to the left hand side equation. The next is orifice. The above is a general form of the pipe flow meter. For the orifice meter, we insert the pipe rate, insert steel plate into with an orifice between two flanks. Okay, so this is two flanks, and we insert a steel plate in between two flanks. Okay, and this is contraction of the outflow water jet. Okay, we can see that this cross area of the inflow, but this is area of the outflow. This contraction we call the vena contracta. Okay, and cross-section area as A2 is smaller than A0, okay, or A1, and A2 is a function equal to C sub C times A0, okay, and C0 is we call the contraction coefficient is less than 1. And due to the turbulent flow, the occurring of the head loss, which cannot be estimated by the theoretical methods. Therefore, the orifice discharge coefficient C0 is used to represent this result. Okay, so Q is equal to C0 times A2 and square root of the pressure. And for C0, we can estimate from real number. And given the real number, we can estimate C0. The range of C0 is between about 0.6. Okay. And the next, the flow meter we call the nozzle meter. This meter is using the same principle as the orifice meter with 3 types. That is the first type, second and third type. Measure flow rate is closer to the Q idea than the orifice because of the smaller contraction, and viscous effect is still exists, representing this effect by using the nozzle discharge coefficient Cn. Okay. And for Cn, we can find Cn from the Reynolds number. Okay, we see that Cn is in the range of 0.94 to about close to 1. Okay, for the nozzle discharge coefficient.